Assalamu alaikum wa rahmatullahi wa barakatuh. I am Hassan Muhammad Zori, student at Imam Abdurrahman bin Faisal. Today, our lecture about Chapter 8, Race Condition, and Chapter 9, Data Sharing Rules, and Chapter 10, Loop Scheduling. Let's get started. First of all, we have normal code without parallel, and in this code, we want to calculate the pi. Here the output is correct, and the time for the code 0.002 second. And after we parallel the code, we use Nivea parallel attempt here for the 4 parallel. It's happen race condition, so it's make the output incorrect, and it's make it more slower than the serial code. Adding a parallel direct breaking out our code and harm the performance. And what is the race condition? What's happening in the previous code? After we add the parallel directs, it occurs a race condition. So we want to explain the race condition. Race condition: multi-thread access and modify shared data at the same time, leading to unpredictable result. Here, as we see, we have multi-thread. At the CPU, we have a core, multi-core, and inside the core there is a thread, and the thread is work for us. So we have multi-thread, it's calculate the pi, and they access the same variable pi, and they modify it and read it at the same moment, same time. So what will happen? It will lead to race condition, and it will give us unpredictable result. So we want solution for it. We have the first solution. We use a critical. A critical ensure only one thread enter a block at the time. So so here we have multi-thread, and here this is the block. There is only one thread will access and will calculate the value, and outside the block the multi-thread also will work. We will force it only one thread can access. So it will lead to protect the block of the code, ensure only one thread can execute it at any given moment. It will protect the section, can create major performance block, and other thread must wait. Here in this code, we add the critical. So when we add the critical to save this line, it will make it safe, but it will be more slower. The output will be correct answer, but very slower. It's slower than the series code, the normal code. So we need another solution. Make a parallel code over 150 times slower than the original serial version. Another solution, we have Atomic. Using Atomic, provide lightweight looking for simple memory update. We will only update the memory side, is more effective than the critical, because it's only protects the specific memory updates for read, modify, and write. It's offer use optimal hardware instruction. In the code, here we add the Atomic for this block. We make it more safe and make it more faster. The output will be correct, but the time for it is much faster than the critical. It is significant improvement, but we are still much slower than the serial code. So we need another solution. The solution, reduction. We use reduction. Eliminate the content by giving each thread private storage. Create a private copy of the variable for each thread. A thread performs their work on this private copy without any locking or content. At the end of the parallel region, they automatically combine the private copy into original share variable using a specific operator like times or maximum, minimum, plus minus. Here in the code, we add the reduction for the by variable and we make it plus. So what will happen? Each thread will take a private copy of the by value and will calculate it, and at the end we will combine each value by using plus operator and we will get the final answer. The output, it will be correct, and the result of it, the time will be as fast as the serial. So when we compare, now we want to compare the performance of the correct result. For the critical, guarantee the correctness, but perform cost is more high. For the atomic, significant improvement for the simple update, but it still involve looking overhead. And for the reduction, avoid sharing memory connection entry, achieve true parallelism and performance. We have solved our race condition, but relying on a quick fix is risky. A true parallel mastery requires consequence control, how every variable is shared or not shared among the thread. So before we use a relay on default, so it's rise for bugs, and we want to use explicit control. OpenMP has default rules for data sharing, but the safest and the clearest code is writing by developer who make their entry explicit. So what we want to do now, we want to make sure what's the variable it will be shared and it will be not shared, when it can be shared or not be shared. So we want to understand data scoping, share and private. First of all, we will talking about the default. For the default variable, the variable declared outside the parallel region are shared among all the threads, and the variable declared inside are private to each thread. Maybe this is will lead us to the bugs. So we need to define it, the variable when it will be shared and when it will be private. For the share, the significant instant variable accessed by all thread require, when we use a share, we require to share, we should to use critical and atomic if the multiple thread write to it, so to avoid the race condition. So here in the code we add a share for the x value, and here the x value is 2, so we'll add the share for the x value, and then we will use a critical to make sure there is no race condition will happening. For the private, each thread gets its own copy, uninitialized local copy of the variable. Changes are not visible outside the parallel region. So here we have y equal 10, and we make it private inside the code for the y variable. So each thread modify its own y copy, and the final answer outside the block, it will be the same 10 without update, because we use the private copy for a specific word, a specific job inside a for loop. We have initializing and finalizing private data. In the private data, we have two types. We have the first private and the last private. For the first private, we need to initializing when the each thread needs its own copy of the variable, but initialize with the value variable head before entering the parallel region. So here in the example we have 30, and in the code we add first private for a var variable. So what's will happen here? Now each thread will start with its a private var 30 and change local inside the block. And outside the block and the parallel region, when we want to print a var variable, it will not change. It will be 30 as the first line we initialize it. It will never change. If we want to keep the value inside here and we want to put it out, what we will use last private. It will retrieve the result. What's the function of the last private? To copy the value of a private variable from the thread that executes sequence last iteration of the loop back to original share variable. So here outside the parallel region we declare var equal 10 and we use last private and make it for the var variable, and the var variable is 10, so 10 it will be come here. But inside the parallel region here the last iteration it will update the var variable to be 5. So outside the region, when we want to outside the parallel region, when we want to print the value of the var, it will be 5, same as it was inside the parallel region. So this is the functionality, and when I can use the last private when I want to keep the last result, and when you don't want to keep it, you can use the first private. Here we have a professional golden rule: force explicit scoping with default none. Default none is one of the most important tools for writing Robin's OpenMP code. It is disable all implicit scoping result, forcing your explicit declare the data sharing attribute for every variable used in the parallel region, reduce bug, prevent accident sharing of the variable that should be private, improve clarity, make the code self documentation. Anyone reading it can see exactly intent use of each variable, encourage carefully design, force you to think about your data flow before writing the parallel code. Here we have two examples before using default none. So the risky is A and B are implicit sharing, so maybe it will lead us to risky or ambiguous or maybe bugs. So we want to fix this, we use default none. So we will force the developer to initialize which variable should be share or private or maybe reduction. So here it's when you use default none, we make share the data N and A, and the reduction will be B. So now we want to go to performance. From correctness to performance, the rule of loop scheduling. Here, let's suppose I have loop iteration, and the loop iteration, it will calculate millions of times. So it will take millions of this. It will take millions iteration maybe, and it will take a lot of seconds. So when you do this sequence, it will take a long amount of time. We will add the scheduling concept using function to the thread. So what will happen? It will make it more fast. Here I have loop iteration. I use scheduled. By using scheduler, what will happen? It will give each thread their job, and they will perform their job at the same time. So what will happen? It will be more fast. Work is divided among a thread is important as what work is done. This is the job of the loop scheduling. It's give us more controls. So showing your schedule strategy static or dynamic or guide depend on when you can use it. we will explain this. So for the loop iteration, we have to schedule it. We have static, dynamic, guide. For the static, what we have here, how to work. Iterations are divided into chunks and default thread in round robin fashion before the loop start, and divided is fixed. So what's the overhead? The overhead low and work is pre-calculate. The work balance poor if the iteration have variable cost, and best for a loop where every iteration takes through the same amount of time. So we have the second one, dynamic. How it's work? Iteration I'll divide the chunks as a thread finish as its chunks it's require another one from center queue. The overhead high and the thread must coordinate to get work, and the work balance good. Natural balance work as fast thread can be take on amount chunk. Best for loop iteration cost unpredictable or very widely. When you don't know the cost, so you can use the dynamic. So now we have the last one, guide. The guide is the hybrid. How it works? Hybrid approaches. It's start by giving a thread large chunks of work, and the chunk size decrease dynamically as loop progress. The overhead modern contention then dynamic with chunk size 1. The work balance good, combining the low overhead start of static with a load balance of the dynamic. Best for loop where there is significant imbalance but also desire to minimize the scheduling overhead. The developer journey to parallel mastery, we have 4 things. Identify the parallel. Parallelism is powerful, but NVIDIA parallelism lead to race condition. So you need to know when you should to parallel and choose the best approaches to parallel to avoid the race condition. And we have mastery correctness first. We have the right tools using, for example, reduction using reduction. And when you use a reduction, you should to use using the right tools for synchronization. Perform reduction for associating operation to avoid looking overhead from automatic or critical. And we have the third one, design for resistance. Control your data environment explicitly. Use private share and other classes with the default none to prevent error and make code entry clear. And we have turn off performance match your loop scheduling using static, dynamic, or guide to your workload characteristics to minimize idle thread and maximize throughput. Effectiveness program is systematic progress. Ensure correctness, build for robustness, then turn for performance. Thank you everyone for your listening.